let us denote the set of parameters by theta. So I am going to come up with some kind of a performance measure for a specific choice of theta. So I will call it eta of theta, right. So for what is a specific choice of theta correspond to? Suppose my theta is like composed of theta 1, theta 2 to theta k. So I give you values for theta 1, theta 2, theta 3 up to theta k. So what does this correspond to? One policy. Okay, when I say I am looking at a specific value for theta, it corresponds to one policy. So when I say eta of theta, that means I am evaluating that policy somehow. Okay. So what is the most natural evaluation measure you can think of for a policy? The expected payoff, right. The expected payoff is the evaluation for the policy. So yeah, so I am going to do that there. Okay. So what is the expected payoff? You know what the expected payoff is? This is the expected payoff I will get for taking action A. This is the probability that I will take action A when I am selecting actions according to theta, right. Right. So this is a standard notation. I don't know if people are familiar with this. This means pi is a function that is parameterized by theta, right, and whatever specific value I give for theta will define what that pi is. Okay, and then this means it is going to take some other argument. Okay, so this is the input to the function, okay, which is defined by these parameters theta. Okay, so this is how when you put a semicolon here, that means it is parameterized forms. Okay. Oh, okay, so your arms are tired from taking all the notes. That's all. Okay, fine. Yeah, so essentially pi a semicolon theta means that is the policy defined by the current settings of parameters theta times the q star a, right, because q star a is a true expectation for taking arm a, right, and then sum over all a, I will basically get the expected reward. But if I am having a deterministic policy, that means essentially only one arm I will take, all the other arms the probability is 0, then the payoff will be q star of that arm, right. Okay, great. Okay, so now once I have this kind of a performance measure, so what do I do is essentially I take theta, okay, right, I take theta, I find the gradient of the performance, okay, so where the gradient is taken with respect to theta, right. So I look at how the performance changes with changing theta, and I will try to move theta in the direction of the increase in the performance. Okay. So this is called gradient ascent. The people might have heard about gradient descent earlier. So this is gradient ascent. So I am going up the gradient, right. If the performance improves, if I change theta in some direction, then I will change my theta in that direction. Okay. Does that make sense? People see this, or do you need more pictorial analogies? Right. So let us say that I have one parameter theta. Okay, let us say I have one parameter theta, right, and that is eta of theta. Okay. Let us say this is my this is a good way to do it. No. Right. Let us say that I have my performance, whatever is an acceptable range of theta. So my performance goes like this, right. So I initially start off with some guess for theta, right, that will be my initial guess for theta, right. Then what I do, I measure this and then I compute the gradient, right. So the gradient is there. So if I look at which direction I should move my theta, so essentially I should move in this direction. So I move a little bit and set that as theta 1, okay. Then I measure the gradient again, okay. Still I have to move in this direction more. So, I keep doing that, and I think I'll declare that I have reached the highest performance there. So, this is essentially how I do it, okay. So, there are a couple of questions which you might ask me here. Why do I have to do this in this kind of an incremental fashion? Why can't I just take the derivative of that and find the highest point and settle down there? Sorry? I do not have the function at all, forget about closed form, I do not have that function at all. What is that function? That is q star a times pi, right. I know pi, but I do not know q star. If I know q star, my problem is solved, right. I do not need to do any of these things. That function itself I do not know, right. So, how am I evaluating this function and trying to find the gradient? By sampling. So, I am pulling a lot of arms, right, according to my current policy pi, right, and then I am trying to evaluate the policy pi and trying to find a gradient at that point, right. So, because everything is done through sampling, so whatever gradient I compute at this point will not be the correct gradient, right. I mean, this is too simple, I mean, it has to either be that direction or this direction, this is too simple, right. But think of a multi-dimensional case when there are many parameters, the right direction you will have to compute can get messed up, right. So, instead of going in all the parameters, instead of identifying the right direction, some parameters you might get the right direction, some parameters you will get the wrong direction, and so on and so forth, right. And therefore, every time you make only small steps, because if you say, oh, I have computed the direction of the gradient, I will just keep moving in the direction until my, or I will take a huge step in the direction until my performance drops or something, that will not work, because the direction itself might be wrong, right. So, in this case, I mean, we have always moved in the right direction every step, but it is possible that because you are estimating the gradient, you might actually make the wrong computations and move in the wrong direction sometimes, okay. So, what really you can hope for from these kinds of methods, which are called stochastic gradient approaches, okay. They are called stochastic gradient approaches because you do not know the true gradient, and every time you make an estimate of what the true gradient will be, and then you are using that for making moves. So, I mean, the most popular form of this will be called SGD, which is stochastic gradient descent, okay. It is a very popular optimization technique nowadays, but in this case you are using stochastic gradient ascent, okay. But still it is the same stochastic gradient idea, and so you have to be careful about how you use it, and the best that you can hope to get is that in an expected sense over many updates, right. I did now I showed you 2 updates. So, if you make this kinds of updates many times, in an expected sense you will move in the right direction of the gradient, right. So, that is the kind of guarantee that typically you expect for these kinds of methods, okay. So, is it clear now? It is clearer now, right. People are not 100% clear about what I am talking, just stop and ask, right. I can elaborate at the risk of slowing down, yeah.
So, how exactly would we estimate the gradient around a point?
Good point, yeah. So, we will come to that. So, we can talk about that. So, if we do not know the function itself, right, how are you going to estimate the gradient, right. So, we will come to that in a minute. So, we know we have a functional form for this. Now, I am going to write down the gradient for this expression, right. This is the expression we have, I am going to write down the gradient for this expression. So, this is assuming that q star a, because it is a parameter of the problem, right, it has nothing to do with the policy, right. As far as your policy parameterization is concerned, q star is a constant, right, because it is something to do with the problem. So, I do not have to do this, I just have to differentiate this with respect to theta, right. So, now I am going to do some hand waving. So what did I do here? I multiplied it divided by pi. Okay. So for this to work, what do I need? Pi is non-zero for all a. So this is one condition that you need for all of this. Any kind of pi that you assume, okay, has to be non-zero for all a. It's just assume some non-zero problem. Now if you think about this particular expression, right, I'll put a bracket around that, right. So what does this remind you of? Does it look like an expectation computation? I am looking at the expected value of some function, right, where I am taking samples according to probability pi, right. This looks like an expected value, right. I am summing over all possible outcomes of a, all possible values here, right, that is the probability. So I am essentially taking the expectation taken according to pi of is it fine? Right. So everybody on board with that, right? So that I can write their expectation. Oh, okay. Sorry about the font. So the expectation is taken with respect to pi. Okay. Is it clear? So now we know how to make an estimate of the expectations, right? How do you do that? We draw sample and then take an average, right? So we can do that. So essentially what I am going to do is pull an arm, that is a sample, right? When I say draw a sample according to pi, that essentially means I have to pull an arm, right? And what happens when I pull an arm? I get a reward, right? But the reward does not figure in here, the expectation of the reward directly figures in here, right? So I can actually write this as a double expectation, you know, I mean the expectation is taken over not only pi but also over the process that generates the reward q star, right? This is also the process that generates the reward. So my sample here is going to consist of RT, right? Is it clear? I mean this is a very subtle thing, if people are with me here on this, is it clear? See, q star itself is already an expectation, right? So instead of, because I do not know this expectation, I will have to estimate this expectation as well, and that can be done by just taking the RTs. So what I will do now is at every time t, I will sample an arm, I will pull the arm, figure out what the reward is, right? But is that sufficient? No, I have to do this, right? So I just can't use the RT directly, I will have to use this also, right? So I will take the gradient of pi, so evaluated at A, divided by the, so this is my one sample, right? This is clear because the expectation I am taking is of this quantity, so the sample that I draw is actually this, right? And I have to do this over, I do not know, some number n, pi AT, you are right. It is fine. So no, I am not using T, I am sorry. So I promised you that I will use n for discrete time and t for continuous time. So we are talking about discrete times here, it has to be n. I do not know if I use t here, sorry about that, but all of you erase in your notebook the t and write down n for this part of the things. Okay, sorry about that. Right. So is this clear? Is there anything missing? Right. So I need to have a 1 by n there. So this gives me the gradient, right. So is this fine? Are we still okay? We are not, because this is actually a estimation. Okay. So I can't put equal to there, it is only an approximation. Okay. Great. So can we compute this? We can, right, because we know pi, we are the ones who determine what pi should be, right, because at the beginning I choose a parameterized representation, right. I can choose whatever, suppose it is softmax, well I know how to take the derivative of softmax, right, or if it is a continuous actions I can just use a, say, a Gaussian, right, I know how to take the derivative of a Gaussian with respect to its parameters, right, or if it is a multinomial, what do? We know how to take the derivative of a multinomial as well, right. So the derivative is very simple. Okay, so I know what form of the function I choose it, so I can go ahead and take the derivative.
We try to estimate q star better, like instead of just taking the reward at that position.
There are a couple of reasons for it. So estimating q star need not always be the right thing to do. Okay, because I have not introduced all the complications, I am hesitating whether I should go there or not. But the thing is, so the q star function sometimes turns out to be incredibly complex, okay, as a function of the state space, okay, not necessarily here, right, as a function of the state space q turns out to be incredibly complex, whereas a direct representation of the policy turns out to be a lot more simple, right. For example, there are many inventory control problems where the policy essentially turns out to be, if the inventory is below a certain level you buy, if the inventory is above a certain level you do not buy, okay. But then the value function itself becomes a very complicated function of how many of the items are left of different types and so on and so forth. So the function itself becomes a lot harder to learn. So there are instances like this where this is easier to learn, right, and there are a couple of other cases, especially when you are talking about very large problems. For example, we will see that policy gradient approaches generalize very easily to problems with continuous actions. So where there are individual actions, so but if I am talking about value function methods, right, where I typically store a value for each action, now I am going to have continuous actions, it is not clear how to handle it. There are ways of handling it, but it turns out that they are not that well behaved as policy gradient approaches are when the action space is continuous, right. So there are many reasons why you want to consider the continuous actions, I mean policy gradient methods. Primarily I would say one of the primary motivations is to handle continuous actions, okay. So this is some kind of a batch updates.
Why don't we try to take the grad by pi thing out of the expectation?
Because the expectation is taken with respect to the pi.
The gradients and the pi, we know the analytical form. Why are we using the samples there instead of the actual?
Yeah, you could do more simplifications of that if you want to, right, but what is your question again?
The expectation is replaced with the sample average.
No, but I need to take this expectation with respect to the the probability distribution pi, right. So and I can't separate this, I can't write this out as a sum, I really can't simplify this further because my q star is here, right. So this is the expectation of this whole quantity. So I really can't split this apart and say that okay, I will just simplify this expectation and take only the expected value of q star A, can I? I can't take E of A B, is it not A into E of B, is it? If A is only a constant, right? Not otherwise. I am not sure that you can simplify this further. Right. So what we are doing here is some kind of a batch mode. So if you think of how we are doing this sampling, so I am taking some theta, fixing it, pulling the arms multiple times, right, fixing theta, pulling arms capital N times, and then taking this average, right, and then computing the gradient and then using that to change the parameters, right. This is one way of doing it. Another way of doing it is say that okay, I will have a theta, I will pull an arm, I will compute the gradient and I will change the parameters, right. So you can have some kind of an incremental version. Right. So where I am saying at every step I will change my parameters by some fraction delta t, I will do this at every step, right. Sorry, so this is what I am doing. So what I am essentially will end up doing is my theta will be theta plus delta theta, right. Theta n plus 1 will be theta n plus delta theta n, right. So this is basically what I am saying. Right. I will do this at every time, for every time I pull an arm I will change this. Right. I mean that is essentially the gradient of the lawn. It turns out this simplifies your life a lot. This observation simplifies your life a lot when you are trying to actually solve problems later, right. Now you can immediately think of softmax becoming very easy to differentiate. I have now taken lawn and there is also lots of e's there, right. So all the e power thing will vanish, so it will become a lot easier to differentiate for you, right. So what I am going to do now is to include another term here rather arbitrarily, called Bn, which we refer to as the reinforcement baseline, right, and adding the Bn should not affect the whole process. Therefore the Bn should not really be a function of theta basically. So it should not be a function of the action I take, right. If it is a function of the action I take, then it becomes dependent on theta. So as long as it is not a function of the action I take, I can keep adding I can add this thing, it is called the reinforcement baseline, right. So one way of thinking about it is when I get a reward, right, I do not know if the reward is a good reward or a bad reward. So giving a baseline and saying that if you are above this baseline it is a good reward, if you are below this baseline it is a bad reward, okay, kind of allows you to calibrate the rewards, right. One typical way in which this reinforcement baseline is used is to just take the average of all the rewards I have obtained so far, right. This is all the rewards regardless of which arm I played, I keep accumulating the rewards, right. Now when I play a particular arm, if it is above this average then it is a good arm, if it is below this average then it is a bad arm, right. So
Valid after some attempts.
valid after,
I mean, if you are averaging after some rewards,
yeah,
usually you can only do that after you have done some setup actions, right? Some initial.
it's fine, eventually it will be all fine, right. So initially you might be making some mistakes because the initial few the B will be wrong, right. So you might actually think a good arm is bad and a bad arm is good, I mean depending, but eventually it will all work out, does not matter, right. So if you think about it, if the reward is good, right, then I will go in the direction of the gradient, right. If the reward is bad then I will go in the opposite direction of the gradient, right. So in some sense that is a little waving here, that but then it is fine. It turns out that adding the reinforcement baseline makes the convergence behavior of this algorithm a little more stable, okay, but it is not necessary. You can, if you are going to implement this, you can do it without the reinforcement baseline also, right. So this is called the and this term is sometimes called the characteristic eligibility. So what is the characteristic eligibility? It essentially tells you,
Why are we replacing Q star A with normal rewards? Why can't we use some expected reward?
if you do that then you get into actor critic. I will talk about that later. Yeah, sure, yeah, you could do that, right, and that is essentially the one of the motivations for getting into actor critic algorithms. So that requires you to maintain a Q star estimates as well as the pi estimates, right, as well as a pi representation. So the pi would be the critic and the Q star would be the actor, other way around, the pi would be the actor, the Q star would be the critic. So that is another class of algorithms, right, which address some of the drawbacks of policy gradient approaches, right. So I will talk about it, but somewhere halfway down the course, not now. So after this I am going to go back and start talking about the full RL problem, and at some point I will come back and do actor critic. Yeah. So his question was, why do I use Rn, right, why can't I plug in Q there, right, you could, and yeah, and typically when you do that it performs better. The algorithm, it is actually it reduces variance significantly at the cost of adding significant bias, right, and yeah, there are other issues, you know what are the other issues going to actor critic, but I will talk about it later, right. Anyway, going back, so why is that called the characteristic eligibility? So if you think about it, so it essentially chooses which of the thetas are most responsible for a change at that point, right. So that is the term that determines, that is the theta dependent term in your updates, right, and it tells you which theta is more responsible for change that is happening here. Suppose there are 3 or 4 different parameters that I have, right. So whichever has the highest gradient, whichever direction you have the highest gradient, that is the direction where the largest change is going to happen, right. So essentially it is telling you which theta is more eligible to receive the update, that is why it is called the characteristic eligibility, right. Does that make sense to people? I think I have lost more people today than in the previous classes. No, great. So this whole thing, right, this way of doing this incremental version of doing this update is actually called the reinforce algorithm. This was first proposed by this guy called Williams in 88. Williams proposed reinforce, in I think in 1988, and in fact he proposed this in the context of neural networks, right. So, when he came up with this algorithm, neural networks were still ruling, right. So, he proposed this in the context of neural networks. He said that your thetas are weights of a neural network, right, and then he came up with this update, and then the biggest contribution he did was he said that, hey, this looks like a really crazy update, right. I mean, how is this going to work, right. Initially people are very skeptical. He actually showed that in an expected sense, that even though I am doing this update after just pulling one arm, okay, in an expected sense the gradient will be in the right direction, right. If I repeat this experiment multiple times and I watch how the weights evolve, right, they will actually move in the same direction as it would have happened if I had computed the correct gradient and then taken steps in that direction. So, essentially he established that for this reinforced update, and since then it has kind of been the one sole hope of convergence for all kinds of complex function approximations and RL. Okay. So, it works really well, but it is extremely slow. Reinforce is extremely slow because the variance is very high. Okay. So, when I want to move on from this, I will talk about the other problems of reinforce. Here is a horrible part about the paper. So, reinforce is actually an acronym. There is an expansion, each letter stands actually for a word. Okay. So, he came up with a name for the algorithm which actually shortened to reinforce. Okay. And that started the trend for convoluted names in the RL community. Okay. So, anyone knows what the expansion of reinforce? Do you know what the expansion of reinforce is? Forgot. Okay. I can't for the life of me. I refuse to memorize what reinforce stands for. Okay. Great. So, let us do some special cases of reinforce, right. I want to consider a binary bandit. Or let us say I take a bandit with two actions, okay, but they can have arbitrary rewards. Okay. So, here is the parameterization I choose. This is essentially the Bernoulli thing, right. So, I have two actions. So, with some probability theta I will select action 1 minus theta I will select action 0. Okay. So, what do I need to do now to get that update rule? I have to find dou ln pi by dou theta. So, what this will be? It will be 1 if A is 1, it will be minus 1 if, correct? No, yeah, look in ln pi, right, it is not dou pi by dou theta, it is dou ln pi by dou theta, yeah. So, it will be 1 by theta if A is 1 and it will be minus 1 by 1 minus theta if it A is 0, right. Can write it like that. Substitute A is 1, so 1 minus theta will get cancelled out, you will get 1 by theta. If substitute A is 0, theta and theta will get cancelled out, you will get minus 1 by 1 minus theta. Okay, very compact way of writing it. And now I am going to say that I will choose my alpha to be some rho times theta into 1 minus theta. So it turns out that as long as your alpha is not dependent on the actual reward that you get, okay, it can be dependent on the theta, this is what Williams showed, as long as it is not dependent on the actual reward, you are all fine, okay, you will converge. So that is essentially this result. So I can make it dependent on my theta, okay. It should not be dependent on the actual action you sampled, okay, and the actual reward that you receive. So as long as that is there, it is fine, alright, and I am going to choose my B to be 0. Why am I making these specific choices? So now let me plug everything back in. So what does my delta theta look like? So alpha n, which is rho into theta and 1 minus theta, into Rn minus B, which is 0, so it is Rn, into dou ln this, which will be A minus theta by theta into 1 minus theta, right. So what do I end up getting? Rho okay. So what is the interpretation for this? Let us say I take action 1, okay, and I get a reward of 1. So what do I get? Rho into 1 minus theta, that is how much I change my value by. So which is essentially this, right, rho into 1 minus theta, right. Suppose I took action, what about I took action 1, right, and my reward was 1, right. What will I do for 0? Oh, that's only one parameter, right. So automatically my other parameter will get adjusted because it is 1 minus theta. Suppose I took action 1 and got a reward of 0, what happens? No change. Suppose I took an action of 0 and got a reward of 1, what happens? Minus theta into Rn, right. So that is essentially what I have here, right. So this is minus theta into Rn, right. So theta is my pi t 80 if you remember, right, and then this is R. So that is essentially what I have. So this is what? LRI, right. So essentially LRI is a gradient following algorithm, actually it is a reinforced algorithm, right. So you can try to look at different choices for the alphas and the different choices for pi, right, and try to come up with this kinds of update rules, right. We will do the softmax action selection as I described in the previous class, right. So do that, right, where I replace all my q's with some arbitrary theta. Suppose I have k actions or k arms, then I will have theta 1 to theta k, these are my parameters, and the probability of selecting arm I will be e power theta I by beta divided by summation over j e power theta j by beta, right. So this is my softmax expression. So derive my reinforce update rules, assuming that is the expression, right. That is one. I am going to give you another homework in the same thing. So I said one of the nice things about doing reinforce is that it allows us to handle continuous actions, right. It allows us to handle continuous action. Actions need not be discrete. So far we have been looking at the cases where actions are discrete. So I am going to use that is my probability distribution, that is my policy, okay. give me the reinforce update rules. So, how many rules will I have for reinforce update rules here? 2, one for the mu, one for the sigma, right. Get me the reinforce update rules, and yeah. So, try to simplify it as much as possible, because when you do the ln mu, I mean the ln pi derivatives, you will get all kinds of weird constants coming there. So, you can choose your alpha appropriately, so that some of these constants get cancelled out, so that I can have I can, just like we did here, right. I chose my rho to be theta into 1 minus theta. Likewise, you can choose your constants in this case also, right, the alphas to be something different, so that you end up with a good nice looking form. Okay, great.